In the previous video, we learned how we can relate all sorts of gas properties together under something called the ideal gas law. You can use the ideal gas law by itself to solve problems, or you can rearrange it to derive the individual gas laws that we covered earlier when you want to predict changes between two different sets of conditions. In this video, we're going to be a little more explicit about how we're actually modeling gases in these laws. It turns out that the ideal gas law and all the individual gas laws are built on something called kinetic molecular theory, which is basically a simplified model for how gases work. Have you noticed that during our whole discussion about gases so far, none of the relationships depended on the kind of gas we were dealing with? This is because, in kinetic molecular theory, all gases are essentially modeled the same way. No matter whether we have hydrogen or water vapor or butane, for example, we treat all the gas molecules like tiny, hard, roughly spherical particles that don't take up any significant amount of space and never interact with each other except when they collide. We also pretend that all the collisions that the gas particles undergo are perfectly elastic, which is a physics thing that basically means no kinetic energy is lost when they collide. This model is definitely a simplification of real life. We know by now that molecules have shapes and volumes that can end up being really important for their behavior, but the assumptions really do tend to hold as long as we're not working under extreme conditions. There are a couple of other gas properties that we can explain using kinetic molecular theory. One property has to do with the relative speed at which gas particles are moving at a given temperature. We've been talking about temperature for a little while now, and we've been saying that it influences how fast the particles are moving. This is true, but temperature is actually a measure of the average kinetic energy in a system. Without bringing in too much physics, this means that the quantity we measure as temperature is really a function of both the particle speed, or velocity in the formula here, and of the mass of the particles. What this means is that if you compare a bunch of different gases all at the same temperature, the heavier ones will have particles that are traveling more slowly, and vice versa. One place that this becomes very relevant is in the measurement of diffusion and effusion. These are two similar properties that basically describe how quickly a gas will either mix with another gas, that's diffusion, or escape from a pressurized environment into a vacuum, that's effusion. Gases made of lighter molecules will diffuse and effuse much faster than gases made of heavier molecules. Hopefully you can get the idea with the simulations here. In the upper chamber, we see that the heavier gas is mixing more slowly on the left relative to the lighter gas on the right. In the lower chambers, we see that the relative rate of effusion is also different at a given temperature for gases with different molar masses. If you want to calculate the average particle speed of a gas directly, there's a handy formula for that, and it's worth writing this one down and examining it for a moment. The average speed of an ensemble of particles like we have with gases is often measured as the root mean square speed, or RMS speed for short. We can see that the formula takes both the temperature and the molar mass of the gas molecules into account when doing this calculation. There's one big thing to watch here, though, and that's that the R value in this formula is not the R value that we used in the ideal gas law. Or rather, it is the same value, but it's been converted into different units that work with this equation. The value to use here is 8.314 joules per mole times Kelvin. And additionally, in order for the units to cancel out properly in this equation, you also have to provide your molar mass in kilograms per mole instead of the normal grams per mole. It's easy to miss those details, so be sure not to forget about them. Finally, if you want to compare the rates of motion between two gases, you can just express the ratio of their RMS speeds. And actually, this reduces down to a really simple function of the two molar masses. This is called Graham's law, and you may want to use this simplified form to solve the appropriate types of problems. We could go into much more detail about these derivations and modeling considerations, but this should be enough for you to start thinking critically about the behavior of gases. Thanks for watching.